So in this video we're going to talk about how to solve polynomial inequalities, and you may have noticed that on the screen you don't have a polynomial inequality, you have a quadratic function. And I've chosen this for a reason, mainly because I want to show you something about the relationship between polynomial inequalities and a function that they are associated with. So let's begin by first talking about this function. What do I know about it from Algebra 1? Well, I know it's quadratic because the highest degree there is x squared, which means its graph is a parabola. More specifically, in this case, it's going to be that happy face parabola, meaning it has a minimum value, and that -4 is a translation. It's one of the transformations. In this case, it's going to drag the whole graph down. When I say the graph, I mean the parent function's graph. So I can quickly sketch this parabola that results from graphing this particular function, and it's going to be terrible because I cannot draw parabolas freehand very well. Okay, that's not symmetric at all. Whew, that's bad. But I know this minimum value here is a -4, and I know my zeros are at 2 and -2. Yeah? So let's look at a very simple polynomial inequality that is actually related to this function. Specifically, x squared is less than 4. Okay, so I don't really need to use any fancy equation solving techniques on this inequality to really figure out what the solution set's going to be, because it's pretty simple, right? I'm just looking for numbers that when they're squared, the square value is less than 4, and I can kind of guess a few that are going to work. Like obviously it's not x can't be 5 because 5 squared is 25. So, but I know 0 works for sure. I know 1 is going to work. I know -1 is going to work. And I know at the values of 2 and -2, I don't have anything less than 4, I have something equal to 4. So that's going to be my boundary, 2 and -2. And these values in between them are going to be the ones that work. So the interval that's going to have my solution set is -2 to 2 exclusive, right? And oh hey, I wonder what happens if when I take this x squared is less than 4 and kind of use some properties of order, maybe subtract off a 4 from both sides. Oh hey, that is the function that I started with. And I wonder if there's a connection between this solution set and this graph. Well, I have this function, x squared minus 4 is less than 0, is equivalent to this inequality up here. And oh look, below the x-axis, I have the values in my solution set. So I wonder if I see the function is less than 0, and it corresponds to the portion of the graph below the x-axis. I wonder what my solution interval would be if I change that less than to a greater than. I wonder if there's a connection there. And obviously there is. I wouldn't have brought it up if there weren't. So let's use some stuff we know about functions to try something a little bit more complicated, shall we? So by slightly more complicated, I mean this. Oh look, I have a cubic experience here. There's a cube there, there's a square there, there's a linear there, and a constant there. And if I had to do anything with this, like solve it or factor it or whatever, I always want to move everything to one side. And this happens to be the very first step you do when you encounter a polynomial inequality, is you want to set one side equal to 0. Okay, just like you do when you solve quadratics with the quadratic formula, or you want to solve by factoring, you got to move everything over. So if I move everything over, I get x cubed minus 3x squared minus x plus 3 is greater than or equal to 0. Now I subtracted everything to the left here because the leading coefficient, it's easier to solve if the leading coefficient is positive and x cubed is positive, so I'm going to move everything that direction. And since it's an inequality, I don't want to mess with multiplying or dividing by a negative because, you know, that I have to switch the direction, so I want to try to avoid that if I can. And so then I have this polynomial that I see a 1 and a 3. Looks like it might be factorable by grouping. And so I see the x cubed and x squared, and I know the greatest common factor there is an x squared. I'm left with an x minus 3. And oh, I want an x minus 3 over here, and I can get it by factoring out a negative 1. Greater than or equal to 0 still holds because all the work is on one side. I'm not treating both sides of the inequality, so I'm not having to deal with the property of order yet. And then I can continue my factoring and get x squared minus 1, and then x minus 3 greater than or equal to 0. And then I recognize x squared minus 1 as a difference of squares. Right? So step 2 was this process of factor. Right? And the whole point of factoring, of course, if it were an equation, would be to find the zeros. And I still want to do that. So step 3 is find your zeros. And so the 0 here is 1, this is negative 1, and this is 3. And the reason why I need to do that is because I want to know something. I don't want to know the zeros necessarily. I want to know what's happening in between them, in those intervals. Because I'm not solving an equation, I'm solving an inequality. So there's going to be whole clusters of answers that are going to work, and I need to know which clusters work. They're not really clusters, they're intervals. Which intervals work? And so I'm going to do, for step 4, I'm going to plot my zeros on the number line. So we're going to plot the zeros on the number line. Okay, so shrink line. I'm going to put my negative 1, my 1, and my 3. And I'm just going to go ahead and write the factored form up here, and then the direction of the inequality I need. Okay, so I'm going to plot these as solid dots because these are where things are equal to 0, and I have the or equal to 0. And so really what I need to do is I need to figure out which one of these intervals is going to give me solutions to this that are going to be greater than 0. And so here's how I do this. Okay, for step 5, we have to test the intervals, because some of them are going to work and some of them aren't. What I mean by work, that means when I plug in a value inside this polynomial, it's going to give me something greater than 0. And I don't have to find the exact value. Since I only care if it's greater than 0, the exact value doesn't matter. All that matters is the sign. I'm looking for values that make this positive because I'm looking for greater than 0, right? And so if I pick a value in this interval, like I'm going to pick a negative 2 here. So when I substitute in negative 2 into each of these factors, what sign results in that substitution? So negative 2 minus 1 is a negative sign, right? Negative 2 plus 1 is another negative sign. And then negative 2 minus 3 is definitely a negative sign. So basically I have 3 negative numbers multiplied together. So the net result of the values in this interval is that I'm going to get a negative result. Okay, so anything from negative infinity to negative 1, when substituted into this polynomial, is going to result in a negative value that's less than 0. So I don't want this interval. This is not part of my solution. And so then I have to test this interval here. And the easiest thing to test is 0, because it's a 0. And so if I plug in 0 into each of these 3 factors, 0 is going to yield a negative value there, a positive value there, and a negative value there. So a negative times a negative is a net result of a positive. And so this interval right here is going to give me, when I substitute it into this, values that are greater than 0. So this interval is part of my solution set. Okay, and so then I'm going to do the same thing in this interval too. So I'm going to choose the value 2 because it's in between 1 and 3. I mean, I could choose a fraction or something weird, but I don't want to. Okay, so if I plug in a 2 here, I get a positive. Plug in a 2 there, I get a positive. Plug in a 2 there, oh no, I get a negative. So I get a net result of a negative value. So I do not want this interval because this is a less than interval, and I'm looking for where it's greater. And so then I have one more interval to test, and that's going to be 4. So if I plug in a 4 to the first one, I get a positive. Second factor, I get a positive. Third factor, I get a positive. Net result is going to be positive, which means this interval here, 3 inclusive to infinity, is also part of my solution set. So that means my answer that I want is going to be inclusive -1 to 1, along with 3 to infinity. Okay, and it just so happens that if I were to graph this function, that relates to it, if I change this greater than or equal to an equal a y, and I had a function that matches with this inequality, its graph is going to do something like this, right? Where anything that was positive is above the axis and anything that's negative is below the axis. So being able to solve these inequalities is going to help me figure out what the graph is going to look like later on. And so to finish off this process, after I test my intervals for their sign, the 6th thing to do is to write my solution. So that's how I solve a polynomial inequality.